Welcome to The Explainer. Today we're doing more than just looking at a bunch of rocks. We're going to dig into geology, the science that really explains, well, everything. The ground we walk on, those mountains way out there, and even the stuff that powers our entire world. And that's the thing about geology, right? It's not some boring class about memorizing rock types. No way. It's about learning to read this epic, and I mean often super violent story of Earth itself. Think about it. Every single layer of stone, every tiny crystal, it's like a word in this incredible story. So, the big question is, where do you even start? Let's jump in and find out what it actually takes to start cracking the code on our planet's biggest secrets, from something as small as a single grain of sand all the way up to a massive mountain range. Okay, so to get a handle on the really big picture, you gotta start small. I mean, really small. It all kicks off at the micro level with the basic building blocks of our planet. And, the detective skills you need to figure out what they're even trying to tell you. The best way to think about it? It's like you're a detective at a crime scene. Seriously. First, you identify your evidence. Those are the minerals, using some pretty simple tests. Next, you classify the rock to understand the crime scene itself, how it formed. And then, finally, you look at the whole structure to piece together the entire story of what went down. So you've got these three main rock families, and they're all part of what's basically Earth's ultimate recycling program. It's called the rock cycle. So an igneous rock, right, it can get worn down into tiny bits of sediment, which then get squished together to become a sedimentary rock. Then that rock can get buried deep down, cooked by heat and pressure, and boom, it turns into a metamorphic rock. It's amazing. Nothing is ever really gone. It just keeps getting transformed into something new. And sometimes, tucked away inside these rocks, you find these incredible time capsules. I'm talking about fossils. And listen, they're so much more than just old bones. They're direct, physical evidence of entire worlds that don't exist anymore. Finding a coral fossil, that tells you, hey, this place used to be a warm, shallow sea. Finding plant remains, you can start to picture this lush, ancient forest and even figure out what the climate was like back then. It's just wild. All right, so we've looked at the tiny clues. Now it's time to zoom way, way out. Let's talk about the colossal, planet-shaking forces that piece this whole massive puzzle together. And the craziest part? These are forces that are still shaping our world, right now, as we speak. Okay, to really start thinking like a geologist, you have to do something that's, it's really hard. You have to wrap your head around this almost unimaginable timescale. It's called deep time. And we're not talking about human history here, not even close. This is a clock that ticks in millions and billions of years. It's mind-bending. And this timeline here, it shows a total revolution in how we think. I mean, we went from believing the Earth was only about 6,000 years old, based on ancient texts, to guys like James Hutton looking at cliffs and going, wait a minute, for this to happen, it must have taken an insane amount of time. But the real game changer? That was the discovery of radioactivity. Pioneers like Arthur Holmes figured out how to use it as a clock, a way to actually measure deep time. And that's what finally showed us the Earth's true, absolutely staggering age, 4.6 billion years. Now this is just a perfect example of science in action. You had this guy, Alfred Wegener, who saw all this evidence. He saw that the continents fit together like puzzle pieces, that fossils from South America matched ones in Africa. And he proposed, hey, maybe they drifted apart. But he couldn't explain how. The other scientists basically laughed him out of the room. It took another 50 years and brand new tech that let us map the ocean floor to finally figure out the how. And that's the theory of plate tectonics. So you see, plate tectonics isn't just some clever guess. It's a rock-solid conclusion that's backed up by all these different, completely separate lines of evidence. You've got magnetic patterns frozen into the seafloor. You've got GPS satellites literally measuring the continents moving in real time. All of it points to the exact same undeniable conclusion. The ground we're standing on is always, always moving. Okay, let's blow this up even bigger. Let's expand our view beyond Earth. Because here's the cool part. The basic rules of geology, how rocks form, how things erode, what happens when something huge smacks into a planet, those rules don't just stop at our atmosphere. Nope, they apply all across the cosmos. So, do the same rules apply on other planets? Oh, absolutely. When we study the massive canyons, the giant volcanoes, and all those craters on a place like Mars, we can use what we know about Earth as a kind of guide. It helps us make sense of the landscapes we're seeing all across the solar system and start to piece together the history of these other worlds. In just looking at the differences between Earth and Mars, man, that tells a huge story. Earth is geologically alive and kicking, right? Active tectonics are constantly churning and recycling our planet's surface. Mars, on the other hand, it's a lot quieter these days. By comparing them, we don't just learn about their two different pasts. We also start to see the incredibly specific, maybe even rare, combination of things that came together to make life possible right here. All right, this brings us right back home. This is the part that connects all this big picture science to you and me. We're talking about how geology deeply, profoundly impacts our everyday lives, our safety, and yeah, the future of our entire civilization. This is where it gets real. Let's be real. We live on a restless planet. That means we have to deal with natural hazards like earthquakes and volcanoes. And geology, it's the key. It's the science that helps us understand why they happen, predict where they're most likely to strike, and figure out the best ways to get ready for them. And you know, the risk from a natural disaster isn't just about how big the earthquake is or how much lava comes out of a volcano. It's all about how prepared a society is. And why does this matter so much? Because when you combine what we know about geology with smart engineering and planning, that can be the difference between an event that we can handle and a total catastrophe. We're literally talking about life and death. Okay, so geology isn't just about hazards, it's also about resources, the things we need to live. And these two words, porosity and permeability, they are absolutely fundamental. Porosity is basically how much empty space, like tiny holes, a rock has. And permeability is how well those little holes are connected so stuff can flow through. Getting a handle on these two concepts is critical for managing everything from the clean water we drink to the energy that powers our cities. And here's where all that theory smacks right into the real world. So think about it. If you need a place to safely store hazardous waste for the long term, what kind of rock would you look for? You'd want something with super low porosity and permeability, right? A rock that's basically a natural vault that will lock that stuff away for thousands of years. This is exactly the kind of massive, critical problem that geologists get paid to solve. So how does all this knowledge and theory and detective work, how does it all come together? Well, it all builds up to one final challenge. You have to prove that you can do more than just memorize stuff. You have to prove you can actually think and solve problems like a real geologist. Yeah, this is so not about just memorizing facts from a textbook. It's about building a powerful toolkit for investigation, for analysis. It means getting your boots dirty out in the field, seeing the evidence with your own eyes, learning to see a flat map is a 3D landscape, and then using your own brain to draw logical conclusions from all that data. And the way you're assessed, it reflects that balance perfectly. It's split right down the middle, 50-50. Half of it is about testing that foundational knowledge, the core principles, but the other half is all about testing your ability to apply that knowledge to a real-world, map-based investigation. Doing exactly what a professional geologist does every day. Because in the end, that's what this is all about. Studying geology isn't just learning another subject in school. It's about gaining a whole new way of seeing the world, a new perspective on the very ground beneath your feet, and finally, understanding the immense, powerful, and truly beautiful story our planet has to tell.